Ave Coders. In this video, we'll continue diving into the necessary theory to further understand how machine learning models work, and this time we'll talk about hyperparameter tuning and regularization. Let's start with hyperparameters. To begin with, why hyper? What is the difference between hyperparameter and a parameter? So in the context of machine learning, a parameter is a certain variable, a certain value that is internal to the model, that is likely to be derived from the data itself. A hyperparameter, on the other hand, is a configuration that is external to the model. Its value is not derived from the data, but it can determine how the algorithm will learn the values of parameters obtained from the data. Essentially, this configuration is set before the model is trained, and subsequently it allows us to control how the model is trained. Let's look at the Titanic example. Suppose we use a small decision tree to determine if the passenger will survive or not. So the first question is gender, male or female. Let's explore the male branch first. The next decision node will be the fare. As you remember from the analysis, people with more expensive tickets most likely had some kind of preference in evacuation, and therefore the survival rate among them was higher. So, was the ticket worth more than $20? If the answer is yes, then we go further down the survive branch. If the answer is no, then we diverge to the not survive branch. This is a primitive example, of course, but it still illustrates the main point I'm trying to deliver. Following this same logic and bearing in mind that among women, and moreover those women who had a first or a second class ticket, the survival rate was much higher. On the female branch, we can directly ask, was your ticket a third class ticket? And if the answer is no, then most likely it was the first or second class, which means that she was likely to survive. But if the answer was yes, then down we go to the not survive conclusion. And now that we have this example in front of our eyes, what is the difference between a parameter and a hyperparameter? As we remember, parameters are internal to the model and are derived from the data. For example, it could be a $20 threshold for the cost of a ticket. Perhaps that was a fare for second or first class, and this was a serious bid for survival. The same logic is reflected in the question of whether the female passenger was a holder of a third class ticket. Okay, we figured out the parameters. Then what will be the hyperparameters in this example? What could be a model configuration that we define before training and that is external to the model itself? For example, for such trees, this could be the depth of the tree. Yes, sounds a bit weird, but let's imagine that the tree starts from the root, Titanic, and grows downwards, a kind of a deep tree. This little tree of ours has a depth of 2. That is, we have 2 levels of branching, 2 questions if you like, or decision nodes. If we wanted to change this hyperparameter and make it equal to, say, 3, then we would have to add another level of branching, which in theory could further help with determining whether the passenger will survive or not. And the choice of features that we used to determine the survival is also a hyperparameter. By choosing features that do not particularly affect survival or vice versa, throwing out those that affect it significantly, we risk getting an indistinct model or an inefficient algorithm, if you like. If we just ask one single question about gender, then our model would be too simple and undertrained. In other words, unable to make a decision taking into account all the factors directly affecting survival. But if we set the tree depth to, say, 10,000, then it is quite possible that our model will remember the fate of almost every passenger, and when presented with the test set, it will get lost because it will be unable to find familiar names. This is what is called overfitting. And the main point is actually to tune these hyperparameters in such a way that this will minimize the total error. This graph is similar to the one we already saw in the other video, devoted to the necessary theory. The blue curve indicates the error on the training data, and the green curve indicates the error on the test data. The x-axis represents the maximum depth of the decision tree, which in this case is a proxy measure for the complexity of the model. And you can see that when the depth of the tree is small, somewhere around 1, then the error on the test and training data is significant. Then somewhere around a depth of 9, we see that the error on both types of data is relatively small. And after that, the error on the test data starts to grow. In other words, the depth of the tree equal to 11, 13, and 15 is probably making the model too complicated. And after that, the error on the test data starts to grow. In other words, the depth of the tree equal to 11, 13, and 15 probably makes the model too complicated and it overfits. The scikit-learn library even has a tool that allows you to determine the optimal hyperparameters, grid search CV, which we'll use in practical lessons later. And now let's talk about regularization, what it is and why we need it. As the deep learning book tells us, regularization is any modification we make to a learning algorithm that is intended to reduce its generalization error, but not its training error. In other words, this is a technique used to prevent overfitting by adding some constraints to penalize an overly complex model. Now it's much clearer, right? Let me just remind you what goal we are pursuing here. In essence, we want our model to be able to determine relationships or patterns within the data, and also be flexible enough so that it does not just remember all possible combinations and can generalize. And at the same time, we want our model to be quite simple because there is strength in simplicity. In fact, a simple model capable of finding the optimal solution is valued much higher than a complex model capable of achieving the same result, because it generally will require a lot more investments in terms of computation and possibly human labor. And as my variation of Occam's razor principle says, if there is no difference, then why should I pay more? And we can say that the purpose of regularization is to limit the model and protect it from becoming overly complex. Let's look at an example from the real world. Let's imagine that you are a chess player and you play well in your home chess club. There you have your favorite chair at your favorite table, not too far from the center, but not too far in the corner either. You play with your favorite set of chess and always open the window to let the fresh air into the room. You are already used to the lighting and your game partners, and then something unexpected happens. You are invited to regional competitions. You arrive at another chess club in a different city, and then you realize that all those things that supposedly influenced your game are in the past. You won't be playing with your favorite chess set, the windows do not open and the lighting is too bright. You have to play with people you haven't played before, and you feel that without all these familiar things you probably won't be able to win as you used to at your home club. But in the end, you take a deep breath and look at the problem itself, and you realize that your success only depends on the decisions you take and moves you make. Everything else, the chairs, the window, the opponents, are just noise. And this is more or less what regularization does. It helps to get rid of insignificant features, leaving only those that directly affect the results. There are many types of regularization, but as always, there are few of the most popular and commonly used ones. For example, L1 and L2 regularizations are like Beatles in the world of regularizations. In essence, they add a penalty to the loss function to limit the coefficients. L1 or Lasso Regularization or Manhattan Distance Regularization imposes penalties for features with large coefficients. In addition, it sets the values of some coefficients to 0, so An insignificant feature can be simply thrown out of the dataset. That is, it actually reduces the noise in the data. L2 regularization or Tikhanov regularization or ridge regression adds squared magnitude of coefficient as penalty term to the loss function. In other words, it shrinks the regression coefficients but never sets them to 0. That is, there will be noise, but it will be so small that the model will have to work very hard to increase its complexity. It is also worth mentioning the dropout. This technique can often be found used in neural networks when, in order to prevent the model from depending on a certain configuration of nodes during training, a certain number of them are randomly excluded. Something like when during training the coach seats several key players on the bench, releasing young players on the field, or even forcing them to play in the minority. Thus, the team learns to play regardless of the presence of star players. Well, this was a little introduction to the necessary theory, in particular such concepts as hyperparameter tuning and regularization. Of course, there are lots of concepts in machine learning, so further I will try to mix them into our practical lessons, so we'll be applying these concepts straight away in code. But for now, please give this video Emperor's thumbs up, toll the bell and subscribe to the channel. That was V, thank you and goodbye.